So the daily is minimum insertion swaps to make a string a palindrome. And it's pretty self-explanatory. We're given a string and we want to know how few characters can we insert to make it into a palindrome. So in example 1, it's already a palindrome, so we just don't do anything. Example 2, I guess this is supposed to illustrate that while visually it is a palindrome, we want it to be like lexicographically a palindrome. So this MBADM, we would want it to be something like MDBA BDM, something like that. And then LeetCode, it's going to be some complicated thing. So this is a problem where you can overcomplicate it. You can think about it too hard. Or you can see that the string can only be 500 characters long. And that opens up a lot of possibilities. Generally, the upper bound for things that will work is like 10 to the 8th operations at most. And if we're dealing with like 10 to the 2.5 operations for every O of n, we could have O of n to the 3rd, and that would be fine. Or we can do O of n squared, and that's what I'll do. So if you think about this, there's a couple of rules that we can draw. So one rule, let's take a word, let's take like Pope, something like that, is if you compare the first character and the last character, reasonable place to start, we can see that they're not the same here. So what can we do? Well, we want to make sure that these are equivalent in some way. So one thing that we could do to make these equivalent is to put an E at the beginning, or we could put a P at the end. And then that way, hey, now there's a last character that matches the first character. Or, hey, now there's a first character that matches the last character. And we could do either of these. We have no idea what's correct. You can kind of see this is probably correct because this immediately gives us a palindrome. But let's say we tried this. Then, okay, cool, the P is satisfied. But now we want this inside string to work. So we just kind of recursively call the same thing. We're like, okay, what about OPE? How long does that take? And then we're comparing O and E. And then we could do the same thing. We could say, well, put an E before the O, or put an O after the E. Let's just say we go with this. And then we're dealing with P and E. And then in this situation, we can just say, well, put the E before the P, or put the P after the E, whatever, and then we have something. And in a situation, let's take the initial string, like ZAZZ, or let's take this one, MBDAM. In this, the first and last characters are already the same, so we can just immediately be like, well, really, we just want the inside to be a palindrome. So what do? We do the same thing. So let's say, put a D there, and then now we're comparing B and A, put a B there, or an A there would work too. And then we're given a palindrome in 2 steps. So it's actually quite self-explanatory. In Python, it's pretty clean too, the code. So we'll attach a cache. This is the dynamic programming part. This is where we say, hey, if you're referencing the same 2 indices, let's say we have some giant string like that, and we're looking at this F versus this J, and we're like, okay, what do we do? Well, we're going to make some choice, and then we're going to make some other choice, and then we're going to get to here, and then at some later point, we're going to compare this I and this S, say. Okay, that's cool, and then we figure out, hey, but like with this substring, what's the best we can do? But then say later on, we're comparing a U and a D, something completely different than that initial F and J that led us to that I and S. Then we're going to eventually reach a point where we recalculate this, but we don't want to recalculate it. We already calculated it. So that's where the cache comes in. This is just like a dictionary, a hash map that says, hey, store the answers to this subfunction that we're about to make. And then if you ever call this subfunction with the same inputs, return the answer that those inputs would give. So we'll just say I and J. Actually, we'll say L and R to make it really explicit. So this is going to be the left pointer and the right pointer. And in the end, we're just going to return DFS 0, length of S minus 1. So we say, inclusively, within these bounds, what's the quickest way we can make this into a palindrome? And this is one spot where we can introduce a little rule, which is if we take this MBDAM example again, there's never ever a situation where you wouldn't want to immediately say, well, really, we're making BAD the same thing. No matter if there's an M in here or whatever, we're never going to not just skip these two M's on either end, because this is just a simpler problem. So with that in mind, the first thing we can say is something like if S at L equals S at R, return DFS L plus 1, R minus 1. Simple enough. If they're not the same, say B and D, then we want to say what happens if we attach a B after the D or a D before the B. But if we think about it, really what we're doing, let's take that example. So the first thing we do is we say, that's great. Okay, get rid of those though. Now we're comparing B and D. If we attached a B here, then, okay, great, the B's now cancel, and now we're looking at A and D. And if we attached a D here, then we would go from looking at B and D to looking at B and A. So really what we're actually doing, we don't even need to think about attaching and changing the string at all. We can just say, okay, either decrement R by 1 or increment L by 1. And then whichever one's faster, do that. So if we had, let's go back to our original MBADM. Let's say we had a bunch of random stuff in here, and we're looking at, okay, MB something DM. Then we have the same choice. We can say, well, okay, decrease D by 1, aka put a D here, but we don't even need to represent that, and then figure out this, or increase B by 1, aka do that, or increase L by 1, I should say, and then figure out this. And whichever one of those is shorter, do that. So in that situation, we can just say something like return min DFS L plus 1 R and DFS R, L R minus 1, and then plus 1, because here we're actually making an insertion to do this. And then we need some sort of base case. So what that'll look like is probably if L is greater than or equal to R, we want to say greater than or equal to, because if we just said if L equals R, here that would be okay. If we're going back to this one, here we would say, well, eventually L and R are both going to wind up at A. That's great. But if we got rid of this, if it's an even palindrome, in that situation, L and R will skip over each other. So we want to safely cover that by saying if L is greater than or equal to R, return 0. And with that, a pretty difficult problem became pretty easy. It's easy to get caught up in the details, but if you have some confidence in the dynamic programming process, then it's not too bad. And if we think about the state space here, if we think about like, okay, well, how many different combinations are there between L and R? There's 500 squared. L could be anywhere between 0 and R. R could be anywhere between L and N, N being the length of S. So in that situation, it's sort of on the order of like 10 to the 5th, which is very fast. They could have had these time constraints be a lot more stringent, and it maybe would have been a more interesting problem, but luckily it was not. Hit like if this helps.